In this last lecture of chapter 3, vectors, we're going to look at two real-life examples of vectors. The first example involves vector addition. So suppose there's a new landowner who wishes to fence in a property that she owns. And this property has a triangular shape bordered by three sides A, B, and C, forming a triangle. Now, suppose she draws out the vector A and then the vector B, knowing both the magnitude and orientation of these two vectors. What she wants to know is the magnitude and orientation of the third side, which is vector C. So how does she find that? Well, here's the thing. You look at this vector triangle. You start from point A, right, which is the beginning of the first vector. Okay, the beginning of the first vector right here. And then you proceed to the end of the first vector. And then you start the starting point of the second vector B from there until you reach this point. And then you start from this point, the beginning of the third vector C, and then you will go back to where you started. So if you think of this as three separate displacements, displacements A, B, and C, then the net displacement is from the beginning of point of vector A to the end of vector C. And that's really the same spot, which means the net displacement is 0, right? So what happens when you add vectors A, B, and C? We get 0, don't you? So that is exactly what I wrote here, A plus B plus C, three vectors add up to 0. So in order to find vector C, you need to know vector A and B. C equals negative A minus B. Okay, so that's the strategy. Let's find vector A and vector B. Find the component expressions for these two vectors, starting from vector A. Now, in order to find the component expression of a vector, we need to know two things. One is its magnitude. So for vector A, that's 80 meters. And then the direction, labeled by the angle between vector A and the positive x direction. Now, how does one define the angle between a vector and a positive x direction? You recall from the previous lecture, this angle, as you can see here, we start from the positive x direction. Okay, we start from the positive x direction, and we go counterclockwise. We go counterclockwise until we land at the positive direction of A. We always start from the positive x-axis, going counterclockwise until we meet the vector A. The angle you get is the angle theta in question. Now, going back to our case, it's a little bit unusual because the vector A points into the fourth quadrant, but the idea is still the same. We're going to start from the positive x direction. Here's the positive x direction. We go counterclockwise. We go all the way until we meet this vector. Right? So this is the angle in question. So we call this angle alpha. So alpha is the angle between the positive x-axis and the positive direction of the vector A. Given the magnitude of A and the angle alpha, what is AX and what is AY? So you see AX, let me write that out, would be equal to A times cosine alpha, right? So AX equals A cosine alpha. And here, A equals 80 meters. And alpha equals to what? Now, this angle is 21 degrees. So therefore, alpha is 360 degrees minus 21 degrees. And that is 339 degrees. Okay, it's not 21 degrees. No, it is 339 degrees. You can also say negative 21 degrees because you're going backwards from positive x direction, you're going clockwise instead of counterclockwise. So you can say you're going in the opposite direction as by convention. So therefore it's negative 21 degrees. It's the same as 339 degrees. Okay, so that's AX, and similarly AY will be equal to A times sine alpha. Right, so you get AX and AY. In the meantime, you can find BX and BY. So what's BX? Well, if the angle between vector B and the positive x direction is beta, then I can write B cosine beta for BX, and BY would be B times sine beta. Right? Now, what is B equal to? The magnitude of B? It is equal to 105 meters according to the diagram. And what about the angle beta? Well, you look at this diagram here, we start from, again, from the positive x direction, okay? From the positive x direction, which is this line here, and we go counterclockwise until we meet this angle. So this is the angle beta. And you can see here, clearly it is 90 degrees plus 11 degrees. So beta would be 90 plus 11, that's 101 degrees. Okay, you can plug in the magnitudes of A and B and the magnitudes of alpha and beta. You can find AX, AY, BX, BY. All right, it's easy to do. Now, how do we write vector A then? Vector A would be AXI plus AYJ. And similarly, vector B would be BXI plus BYJ. And then as far as vector C is concerned, that's what we really want to know. Vector C is equal to negative A minus vector B. So that is negative AXI plus AYJ, and then minus BXI plus BYJ, right? BYJ. Okay, and you can just plug in what AX is, what BX is, and I can put all the X components together. That's AX plus BX. And you have I here, and then minus AY plus BY. J. Okay, you can find the numerical values of AX, BX, AY, BY easily by plugging the values of A, B, and alpha and beta. And if you did that, you are going to get, okay, I'm going to spare you the steps of numerical calculation. Just plug the numbers yourself. It is equal to negative 55 plus 7i, and then minus 74 plus 4j. Everything is in meters. Okay, don't forget the units. All right, so you can see, C has a negative X component and negative Y component, which means it should point into the third quadrant. And is that right? Well, look, this is pointing, C points this way, right? So it is in the third quadrant, okay? And it says the magnitude of C is, well, we're gonna find out. Okay, we haven't figured that out yet. They're looking for the magnitude, the length of C, and also the orientation. So let's find the magnitude of C first. That's easy enough to do. C is the square root of Cx squared plus Cy squared. That's the magnitude of C. Cx is negative 54.7. Cy is negative 74.4. So you plug in these numbers and you're going to get 92 meters. Okay, so the length of C is 92 meters. And if you look at this diagram here, look, A is 80, B is 105, and C should be, because it's 92 meters, it should be somewhere in between A and B. That's precisely what you can see here. So qualitatively, roughly speaking, it looks like it's the right length. You know, it's in the right ballpark at least. Okay, and next thing you want to know is the orientation of C. You can find that, we can get that from the angle theta right here. Okay, now C points into the third quadrant, right? So this is C here. And if I were to draw a coordinate system, then I would get something like this: X and Y, positive X and positive Y. So that's why you know, both the X, Y components of C are negative. Okay, but as far as this angle is concerned, how would you find this angle? Well, if you take the vector C and break it down to X, Y components, this would be Cx and this would be Cy. Okay, so you have Cy, you have Cx, right? And this angle theta, as according to the diagram, is this angle we're talking about. So clearly, if you know how long this side is, which by the way is just the length of CX, and that side, which is length of CY, you can find the angle. Tangent theta equals CY over CX from this diagram. So let's do that. Let's find the angle theta. Okay, tangent theta equals CY over CX. In fact, both CY and CX are negative, so that cancels out. CY equals negative 74.4 meters. CX equals negative 54.7 meters. So, and if you do that, you can find the angle itself by taking the taking the inverse of tangent. So that's there. And you can plug in a number CX, CY, you will get the angle to be 54 degrees. You can verify these numbers yourself. And so this angle theta is 54 degrees. Does that look roughly right? Yeah, look at this angle here. This angle here, doesn't that look a little bit over 45 degrees? Okay, so qualitatively, we got the right answer. And that is how we can find the vector C, which closes this property completely. And you can see here, I didn't have to draw precisely. The drawing they gave us is actually pretty precise to scale, but we don't have to draw it precisely. Just have to know the information, the numerical numbers, values 80 meters, 21 degrees, 105 meters, 11 degrees. Even if you didn't draw that very well, you can still find CX and CY accurately. You can find the magnitude and the orientation of the vector C accurately, given these numbers. So this is a real life example of how to add vectors up. Okay, now let's look at a second example, which is quite fascinating. It is also a real world example, but it's on a much bigger scale. What you see here is a piece of equipment that was brought by the astronauts of the Apollo 15 mission onto the moon. They positioned this module on a certain spot on the lunar surface. Okay, this spot, this module here, and you have, it's like a honeycomb structure with all these little wells. What are these? Well, this gadget is what's called a retroreflector. What is a retroreflector? It's an optical device such that when a beam of light shines upon it, it reflects the light precisely backwards into the same direction. Okay, so if I had a retroreflector, then wherever I am, I can shoot a beam towards that retroreflector and I would receive that beam right back at the same spot. It doesn't go reflect to somewhere else. And that is useful because we can then measure the distance between the Earth and the moon by positioning a retroreflector there. And then I shoot a beam of laser towards that retroreflector, knowing precisely where it is. And a beam of laser would just reflect backwards. Now, if you can measure the time interval between the incident laser beam and reception laser beam, then you can find the distance between the laser emitter and the moon, because laser is a form of light. It travels at the speed of light, right? So the time interval from the emission of the light beam to reflection light to reception light beam is just twice the time it takes for the light to travel between the Earth and the moon. And if the speed of light is c, then c times delta t over 2. Why delta t over 2? Because delta t is the total time. You have to take over 2. That's the time for one way for light to travel between the Earth and the moon, one way. That would be equal to what? The Earth to moon distance, t. Okay, distance equals speed times time. Now, light travels extremely fast, but don't forget the Earth to moon distance is also quite large. Okay, as a matter of fact, the Earth to moon distance, roughly speaking, is about 380,000 kilometers, and the speed of light is 300,000 kilometers per second. So it takes a little bit over 1 second for light to go from the Earth to the moon. Okay, so therefore the back and forth time is a little bit under 3 seconds, which is measurable. If you can measure that delta t precisely, and of course you know the speed of light precisely, then you can locate the distance between the Earth and moon precisely. And over the over the years, astronauts have positioned different reflectors on different parts of the moon, and you can see here on this picture, these are some of the reflectors they put on the moon. And here on Earth, they have those base stations, which would project a powerful beam of laser and aimed at one of those retroreflectors. Again, the beauty of it is that no matter where the station is, okay, no matter how the laser is aimed, the reflection is right back. So at the same station, you will receive the signal. It's not like the reflector, you start from Hawaii and reflector goes to Italy. It's nothing like that, okay? At the precisely the same station, you will receive it. That's why it's called a retroreflector. So if you shoot a beam in a different direction from this angle, it's also going to go reflect right back. Okay, so it's always the same station will receive the signal. That's why it's called a retroreflector. Now, believe it or not, the laser beam is strong enough so that after getting reflected by this reflector on the moon, when it comes back, we can still receive it. Okay, and we can measure the time delta t precisely, so we can measure the Earth to moon distance to a high degree of accuracy. Here is a list of some of the Earth stations that sends and receives laser beams to measure the Earth to moon distance. For example, the first one is based in Texas, and it was in operation during these 2 time periods, and so on. And there are accuracy readings for this guy, for example. This is the accuracy reading for this guy that was former Soviet Union. The station is based in former Soviet Union, and the accuracy is between 3 meters and 60 centimeters. Wow, we're talking about the Earth to moon distance. Okay, a vast separation, and you can measure it to such a great precision. It's incredible. But this one is even more incredible. This station is based in Hawaii. So you shoot a beam of laser from the Hawaiian station to a reflector on the moon and comes back. You measure the time so accurately that you can find the Earth to moon distance with an accuracy of 2 centimeters. Just amazing. So that's how it works. But we haven't answered this question, and that is, how come it reflects the light right back? And normally shoot a beam of light towards a mirror. By tilting the mirror, the reflected beam can go different directions. It doesn't have to get precisely back, right? How does this one guarantee a reflection right back to where you came from, regardless of which direction the light comes in? Well, the physics is actually very simple. Okay, in each of these little well-shaped areas, what you really get is a corner reflector. Now, what is a corner reflector? This is a corner reflector. It's really 3 mirrors, 1, 2, and 3, and they're mutually perpendicular to each other, forming a corner. So this is the tip of this corner here. Okay, and as you can see, this black beam of light coming through gets reflected by mirror number 2 here, and then by mirror number 1, and then by mirror number 3, it comes out precisely back in the same direction. Same thing happens to this red beam of light. It comes in, this time it's getting reflected by number 3 first, and then by number 1, and then by number 2, it also comes out at precisely the opposite direction. So why is that? Well, we're going to use our knowledge of the reflection of light and the expression of vectors, vector components, to understand what is going on. All right, so you have to understand how light reflects. Suppose I have a beam of light reflecting on a mirror. This mirror is in the so-called XY plane. Okay, so we have a XY plane. Here's a mirror. Okay, so this is the z-axis perpendicular to the XY plane. So here's the z-axis. Okay, the XY plane is the one I draw. What I draw is a cutout of the XY plane. So this is the X direction. The y-axis actually perpendicularly sticks out of the screen. Okay, right. So that would be the y component. I cannot draw it here. It's not 3-dimensional. Now suppose I have a beam of light coming in like this. coming in like this. The law of reflection that you will see in detail in physics 8b tells you this. It tells you the reflected light is in such a direction that the incident angle, which is the angle formed by the incoming light ray I, and the z-axis, which is normal to the surface of the xy reflector, this angle theta I incident equals the reflected angle theta r. Theta r is formed by the normal to the xy plane, which is the z-axis, and the reflected light. So these two angles are the same, okay? Theta I equals theta r. Now, the way I draw it, this incoming beam, if I use a vector to describe the direction of the incoming beam, it doesn't have any y component. I'm assuming it's within the xz plane. It doesn't have any y component. Okay, that's a special case. So if I would write the component expression of the incoming vector, then I would get something like this. I would get an x component and I would get a z component. Okay, here's the x component. So this vector is like this, right? Here's the x component. It goes out like this, and here's the z component. Now let's look at how the reflected light ray look like. Here is the outgoing vector, and you look at the x direction. The x direction is like this, and the y direction, I'm sorry, the z direction is like that, right? Now, since these two angles are equal, the incoming and outgoing angles are equal. All right. This angle and that angle, they're the same. That is telling me that the x component, this component, and this x component, they're really the same. Okay? Because if you take this guy, which is x component, divided by the magnitude of the outgoing beam, of the vector representing outgoing beam, you get sine of this angle. But for incoming one, again, this is the same as that. That's the x component, and that is the incoming beam's magnitude, which is, I just call it 1 unit. You get this angle, but this angle is the same as that angle. So really, the x component is unchanged. Okay, so x remains unchanged. So if I have the incoming vector as xi plus yj plus zk, I have xi plus yj plus zk. That's the most general expression, right? Look at the outgoing. The outgoing one is still xi. The x component doesn't change. Now, what about the y direction? The y direction is non-existent. It's 0 in this case. Okay, right? It's only the beam lives in the xz plane. So it's plus 0 plus in the z direction. Now, be careful here. The incoming component in the z direction goes downwards. Now the outgoing has the same magnitude, but it goes upwards. So z direction is being reversed, negative zk. Okay. Now, if you look at it, you'll find that not only is the x component unchanged, the y component is also unchanged because it went from 0 to 0. Okay? The only thing that changed is the z component. So you wonder, what is the difference between z and xy? How come the z component is reversed, yet the xy components stay the same upon reflection? Well, it turns out that z is different from xy. Xy is the plane in which the mirror is located. Right? The mirror is in the xy plane, right? Z is different because z is perpendicular to xy. So what does that tell you? If you position a mirror in the xy plane, then you shoot a beam towards this mirror and get reflected. What happens? The xy components of this beam do not change, but the z component gets reversed. Okay? What happens if you have a beam, you have a mirror that's in the yz plane, perpendicular to the x-axis, then you shoot a beam towards that mirror in the yz plane, then what happens? Well, this time the yz component should stay the same and the x component is reversed, right? Make sense? Now, suppose I have a beam coming in with a vector is of xi plus yj plus zk. If you want to reflect this beam precisely backwards, then what you need is to reverse all 3 components, right? You want to go from xi plus yj plus zk to what? Negative xi minus yj minus zk. That's what you want. So if the incoming vector, by the way, let's give it a symbol, we call it n, okay? So n is given by this. So you want n to become what? Negative n. That's what a retroreflector does, right? So you want to precisely go back in the opposite direction. Then that means you want, so xi plus yj plus zk will have to become what? Negative xi minus yj minus zk. And that will accomplish it, right? So you want to reverse all three components. Question is, how do you do that? Well, how does one reflect? How does one change x to negative x? Well, from what we did, the analysis we did here, in order to reverse the component x, what you need is to have a mirror positioned in a YZ plane so that it reverses the x component perpendicular to the YZ plane. Okay, so you would, to get this negative sign here, you would position a mirror in the YZ plane. Now, so let's draw an XYZ coordinate system, okay? So you have, we call this X, we call this Y, we call this Z. In order to reverse the X component, you need to position the mirror in the YZ plane. So here is one of the three mirrors you must have, okay? So here's, you put a mirror here, put a mirror like this. Let me use a different color for the mirror. You put a mirror here, okay, like this. So whatever beam that shines upon this plane will get X component reversed. Now, how does one change Y to negative Y? We need to reflect off of what? The XZ plane, right? So you need to position a mirror in the XZ plane, and this is the mirror we're installing, okay? And finally, you want to reverse the Z component. And that, of course, as we saw right here, you need a mirror in the XY plane. So here's the mirror in the XY plane. So we have a beam of light coming in, and when it hits all three planes, all three mirrors, it'll get reflected by all three, and therefore it's going to reverse X, Y, and Z. That's why n becomes negative n. It's just how simple that is. That is why you need to form what's called this reflecting cube, okay, or reflecting corner. And that's how we reverse everything. Does that make sense? Well, some of you might think, what if the incoming beam only hits two mirrors? It never bounces off three mirrors. Doesn't that leave the third component unreversed, right? If you don't hit a mirror, that component perpendicular to it will not reverse, right? Let's say, for example, you have a beam coming in. It never hits this mirror here. It never hits this. It never hits this mirror, the YZ mirror. Question is, how come it never hits the YZ mirror? That means it moves parallel to the YZ plane. That's why it never hits the YZ plane, right? Now, when you are parallel to the YZ plane, so you're coming in like this, right? You're coming in like this, parallel to the YZ plane. So you never hit the YZ plane. But if you are parallel to the YZ plane, do you have any X component? No, you're perpendicular to the X direction. So the problem with not hitting the YZ plane is that the X component will not reverse. But what is the X component you have to begin with? It's 0. Okay. Now, do you have to reverse 0? No, because you reverse 0, you just get negative 0. It's still a 0. Do you have to change 0 to negative 0? No, it doesn't make any difference. Okay, so therefore, it doesn't matter if it hits only 2 planes, because that only means the beam is perpendicular to the third plane. And you can also argue what happens when the beam hits only 1 plane. That's even more special. That's because the beam is perpendicular to the other two, parallel to the other 2 planes. So there's no reason to reflect the other 2 components, because those components are 0 to begin with. So you have a beam coming in with Xi only. Okay, Y is 0, Z is 0. So this will become negative Xi. That's it. Y still stays at 0. Z still stays at 0. So that's how it works. However many planes it hits, it doesn't matter. n becomes negative n, and you are precisely getting the signal back to the same spot. So this is really cool. Now, does this only work as lunar reflector? Okay, no. It has many applications on Earth, for example. You see this right here? This, in fact, is a gadget for reflection of radar beam. So you get a beam of radar signal coming in, which is actually a microwave, comes in and comes out at precisely reverse direction. Because again, you have three corners. You have three mutually perpendicular reflectors. This time it's not mirror for optics, for optical mirror. Rather, it's just a piece of metal, but it acts as a reflector for the microwave. So 1, 2, and 3. They are mutually perpendicular to each other. Okay, and this is even more interesting because what you see here is a reflector off of a bicycle. You'll also have reflectors like that for the taillights of a car. And if you take a closer look, you see this tiny honeycomb structure like this. And guess what? Each one of them is a corner reflector, just like here. Each one of these is a corner reflector. Okay, so it's the same physics that you see both on the moon and here on Earth. That is quite nifty. So these are two examples that I wish to give for the application of vectors in real life, and there are countless other applications, as you will see throughout the rest of this class, along with the rest of the entire physics series.